Hello everyone, welcome to my lecture series of electromagnetic fields. We will discuss different theories, phenomena and numerical solution of different cases in this series. I hope this series will give a fruitful outcome to physics scholars or engineering students. In a previous video of this lecture series, we have derived an expression for electric field intensity due to finite line charge and a charged circular ring. In this video, we are going to derive an expression of electric field intensity due to infinite sheet of charge. So let us begin. So consider an infinite sheet of charge placed on xy plane with uniform charge density rho s coulomb per meter square on it. Then assume a point P on z-axis at which the intensity is to be determined, and the location of point P is on the z distance from the origin on the z-axis. And now assume a differential surface ds which carries a charge dq and a normal direction to ds is z-axis. So the fundamental logic behind this is, first we are going to determine the field intensity due to a small surface, say differential surface ds on point P, and then we are going to take a surface integration over the whole surface. Fine. So for that purpose, first we will only calculate for the surface ds and then we will integrate the result. Here cylindrical coordinate system will be more suitable for the derivation, as the sheet can be imagined as a part of cylinder and every point of the sheet can be easily represented with the help of cylindrical coordinates. See, you can adopt any coordinate system for the derivation, fine, but the one which gives the minimum calculation efforts is the best suitable over here. So for this case, the cylindrical coordinate system is more suitable. However, we are going to use cylindrical system. We have shown x, y and z axis of Cartesian coordinate system as well. Fine. So as we have discussed, the infinite sheet of charge is placed on xy axis, xy plane. So you can imagine an infinite sheet. See, it is not bounded anywhere. Fine, it is still expanding up to infinity. Okay, so this infinite sheet is placed on xy plane, as you can see, and the charge density on this sheet is rho s coulomb per meter square. Now we want to determine the field intensity, say on point P over here, which is placed on the z-axis at the distance small z from the origin. So this point is our origin and point P is displaced by small z distance on z-axis. And now in order to determine the intensity on point P, we are assuming a small differential surface, but here we are going to use cylindrical coordinate system, so the shape of differential surface will be of cylindrical coordinate system. So here we are assuming a small surface ds which is displaced by distance r from origin. Here I have shown this on x-axis so that the value of phi in the position vector of ds will be 0. Fine, you can show it anywhere, fine, but in this case you also need to consider some non-zero phi. Fine, so it will increase our calculation effort, so we are not going to perform that. Okay, ultimately we are concerned with the final results only. Fine, so we will try to keep our calculation as easy as possible. So I have shown this differential surface on x-axis. Now this is our position vector P. Position vector of point P in cylindrical coordinate system can be represented as, so as you can see, the point P is on z-axis, so the r coordinate will be 0, so we can write 0 ar bar. It is not making any angle with x-axis, so again phi coordinate will also be 0, so 0 a phi bar, and it is at the distance small z on z axis, so z component will be z az bar. So this is our position vector of point P. Same way we need to produce a position vector of our differential surface. So as you can see, the position of our differential surface in cylindrical coordinate system, so it is displaced by distance r from the origin, so its r component will be small r. As this surface lies on x-axis, that means the angle between x-axis and this ds is 0, so again phi component can be 0, and this is the reason why we have taken this element on x-axis. And this plane, this infinite sheet, is laid on xy plane, so it will have 0 height, so its z component will be 0. Now we have the position vector of both the point of interest P as well as the differential surface ds. And if we want to determine the distance vector, so the distance vector here, capital R, is nothing but Rp minus Rds. So we will subtract the position vector of ds from the position vector of point P. So doing so, we will have minus R AR bar plus Z AZ bar. So this is our distance vector R bar. Now the direction of field intensity due to ds on point P will be on the direction of distance vector. So we can represent that direction with the help of unit vector. So let the unit vector in the direction of r be AR bar, then AR bar can be determined by dividing distance vector with its magnitude. Doing so, we will have minus R AR bar plus Z AZ bar divided by the magnitude of same. Now the magnitude of this distance vector is nothing but under root R square plus Z square. So we have determined the direction also. Now the formula for intensity will be dq, that is small charge on this differential surface, so dq divided by 4 pi epsilon 0 modulus of r bar square into AR bar. So we are having almost each and every value to be put in this equation. Okay, still we don't have the value of dq. Now see, this surface is directed along z-axis. Fine. So the formula of differential surface directed along z-axis, we can write ds bar equals to, see this length, here there will be some difference in angle d phi, here it is some difference in radius, that is dr. Fine. So this length will be r d phi. Now the difference between radius will be dr, and the direction of this surface is z direction. So among the 6 differential surfaces that we have seen in cylindrical coordinate system, you can also refer that video if you wish to. We are going to use this equation for given differential surface. Fine. So if ds is defined in this manner, then a small charge dq on this surface is nothing but rho s into ds. So if we multiply rho s with this, then it will be rho s into r dr d phi, or say here only magnitude is concerned, so because charge is a scalar quantity, so rho s ds, so our small charge on differential surface will be rho s into r dr d phi. Okay, so now we are having each and every value to be put in the equation. Let us give it equation number 1. So putting all the values, sorry, here we can represent the direction of intensity due to ds on point P, and we are going to divide that intensity into two components. One component along the direction of R and second component is along the direction of Z. Fine. So moving further and putting all these values in this equation 1, we will have dE bar equals to simply rho s into r dr d phi whole divided by 4 pi epsilon 0. Now the magnitude of distance vector square, so we can write under root r square plus z square whole square, and the unit vector along the direction of distance vector can be written as negative r ar bar plus z az bar whole divided by under root r square plus z square. Now we need to take the surface integral of this equation in order to find the field intensity due to whole surface charge. Okay, but before doing so, if we can have a small differential surface in positive x-axis, then such small surface may also be imagined on the same distance r in negative x-axis, and due to this surface we are going to have some small field intensity on point P, and if we divide this intensity into two components, one along R and other one along Z, then we can witness that R component of both the intensity will cancel each other. Fine. So here no component of field intensity will exist along the direction of R. Okay, because for any particular differential surface we will find an same surface in opposite direction which will cancel out its R component, and only Z component will be there. Okay, because this sheet is spreaded infinitely. Okay, and that is why we can eliminate this term negative r ar bar from the calculation. However, if you do not neglect this term and you keep it in your calculation, then at the end you will have the same result. Fine, but your calculation efforts and time will be more. Okay, so in order to reduce the time and efforts, we are going to utilize the equation rho s r dr d phi whole divided by 4 pi epsilon 0. Here again, now this under root r square plus z square whole square is nothing but r square plus z square. If it is multiplied by under root r square plus z square, so if it is multiplied under root r square plus z square, which is nothing but r square plus z square raised to 1/2. So in this case, this multiplication will turn out to be r square plus z square raised to 3/2. Okay, so this is nothing but the calculation of power. So putting this value in the denominator by multiplying both things, so we here have r square plus z square raised to 3/2. Now this negative r ar bar we are going to eliminate from the calculation, so the only available component will be small z az bar, and now we are going to take the surface integration. But doing so, we can find the intensity on point P due to this infinite sheet of charge. So we are going to take double integration, because see here the reference variables are 2, r and phi. So we know for infinite sheet the radius of cylinder will vary from 0 to infinity, and the angle will vary from 0 to 2 pi. So these are our limits for the integration. Rho s r dr d phi divided by 4 pi epsilon 0 r square plus z square raised to 3 by 2 z a z bar, or you can put this z over here in numerator also. Fine. So here in this step we can witness that the integration is going to be very tough, because when we will see the integration with respect to phi, it is very easy because there is no component of phi in the numerator or denominator. So it will be integration 1 with respect to phi, so it will be phi itself. Fine. The issue is when we will calculate the integration with respect to r, because we have a r in numerator and r square plus z square raised to 3 by 2 in denominator. So it is going to be very cumbersome calculation. So again, what we will do here, we will take help of variable manipulation. So in variable manipulation, let me write the equation. So r equals to 0 to infinity, phi equals to 0 to 2 pi, rho s z r dr d phi whole divided by 4 pi epsilon 0 r square plus z square raised to 3 by 2 az bar. So here we are taking r square plus z square equals to u square. So we are assuming that r square plus z square equals to u square, and that is why 2r dr equals to 2u du, or further we can also write r dr is equals to u into du. Now if we have taken any variable manipulation, then our limit of integration will also be changed. So where r equals to 0, that is lower limit, implies u equals to z, and when r equals to infinity, at that time u will be equal to infinity itself. Okay, so adopting this manipulation in our equation number 2, let us give it as equation number 2, then this equation will now become e bar equals to integration 0 to 2 pi integration. Now this manipulated limit has been changed from 0 to infinity to z to infinity. This is the limit of phi, 0 to 2 pi. Then rho s, no change will be there. Z, again no change in z, but here r dr can be written as u du. So here will be u into du. d phi will be as it is. In denominator, 4 pi epsilon 0 being constants, it will have no change. R square plus z square, we have assumed that this is u square. So putting here r square plus z square equals to u square, then it will become u square raised to 3 by 2, which is nothing but u cube. So here you can directly write u cube. Fine. So simplifying the terms, this will become now u square. Fine. And performing the integration, E bar. So we can detach the integration with reference to phi as phi from 0 to 2 pi. Now this rho s being constant, z distance being constant, 4 pi epsilon 0 are also constants. So they will come out from the integration operation. Here the only integration will take place from z to infinity 1 upon u square du. Now putting this upper and lower value in this first term, we will have 2 pi. So our next equation will become E bar equals to 2 pi rho s into z divided by 4 pi epsilon 0 integration from z to infinity 1 upon u square du. Now simplifying this, we will have here rho s z upon 2 epsilon 0. Now the integration of 1 upon u with respect to u is nothing but integration of u raised to minus 2 with respect to u, and this integration will be u raised to minus 2 plus 1 divided by minus 2 plus 1. Doing so, we will have u raised to minus 1 divided by minus 1, which is nothing but minus 1 upon u. Fine. So for studying electromagnetics, your mathematical concept and mathematical logic should be very strong. Fine. So performing this integration with its limit, we are having rho s into z into in the numerator and 2 epsilon 0 in the denominator, and this integration will be minus 1 upon u. Lower limit is z, upper limit is infinity. So and az bar, here az bar represents the direction of field. So as you can see over here, putting the upper and lower values, we will have rho s into z upon 2 epsilon 0 minus 1 upon infinity minus minus 1 upon z. So 1 upon infinity will be 0, and here minus minus will be plus. So plus 1 upon z will be multiplied with rho z upon 2 epsilon 0. So z will be cancel out. Okay, let me write one more step. The simplification of this square bracket will be 1 upon z. So here z will get cancel out, and we will have the final equation as rho s upon 2 epsilon 0 az bar. Or in general word, if this infinite sheet is not laid on xy plane, but it is laid in any arbitrary way in 3-dimensional space, then in general we can write E bar equals to rho s upon 2 epsilon 0 an bar, because the field will only exist in the normal direction of the plane. Fine, it will have zero existence along the span of sheet. Okay, so we are going to have the effect of field intensity in the normal direction of infinite sheet. So we can use this result almost in any case, fine, to solve any numerical. Fine, here the unit of field intensity will be Newton per Coulomb or volt per meter. Okay, but some important observation that should be discussed, that E bar due to infinite sheet charge at any point is not dependent on the distance. See here the distance is z from z of point P from the infinite sheet. Fine, but in final equation we are not having any term of z. So at any point the value of intensity will be constant, and that value will be rho s upon 2 epsilon 0. See here our point P is on the upper half of the plane. Fine, so the intensity will be in the direction of az bar. If our point P, say it is somewhere under the xy plane, say over here we have p prime, fine. So in this point the direction of intensity will be downward normal, so this direction will be negative az bar, fine, because due to such infinite sheet the field will be normal to it anywhere in the space. Okay, so no doubt the direction of intensity will depend on the location of point uh, in either half of the infinite sheet, but the magnitude of field intensity will always be same, and which will be equal to rho s upon 2 epsilon 0. So I hope you got the point, and you should remember some variable manipulation techniques in order to ease your calculations. Thank you.